SwayamPrabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 21. We were talking about frictional losses in realistic situations where wall friction would play substantially a big role in determining the energy balance, particularly in case of sprues and runners, and that with bends and fittings. So we are going to look at a problem example today where we would like to do this calculation. So there is a gating design for a mold which is 50 centimeter by 25 centimeter by 15 centimeter as shown in this figure right here, and the cross sectional area of the gate is about 5 centimeter square, which has been given here, and you have to determine what is the filling time for this design by including now the frictional effects and the velocity distribution effects particularly. So the liquid being poured is molten iron with the properties of liquid density or liquid metal density about 7800 kg per meter cube, kinematic viscosity eta about 0.00496 kg per meter second, and for a 90-degree bend, as you can see right about here in this particular down sprue, the L by D equivalent which has been obtained from standard data is 25. So that is the contribution to the wall friction effect because of the bend. Obviously there will be a bending effect because of which there would be an energy loss. So these all terms have to be taken together to compute the CD. So it should be noted that to obtain the beta value, which is actually the distribution function, the kinetic and the velocity distribution, the energy loss because of the velocity distribution function, and also the friction coefficient F and the EF, which three of them are very important for determination of the CD. So we should determine the flow as either laminar or turbulent. So this calls for an iterative process So iterative because at the outset you have to sort of find out that without including all these frictional effects what is going to be the range of the velocity, and then from there you look at whether the velocity range corresponds to a laminar range or a turbulent range, and then try to estimate the different factors beta f and EF using that strategy. And so as a first approximation, the average velocity is computed with an assumption of the CD value being equal to 1. So obviously the V3 average velocity would be twice GHT whole under the root, and in this case, as we had calculated before, the H being equal to this 12 centimeters, we have a V3 value which is approximately 1.716 meter per second, and this I think we had calculated in one of the earlier modules where we talked about no wall friction and only an idealized condition. So now the gate region has a total area of 5 centimeter square, and if we assume the gate diameter to be d, we can say pi by 4 d square is actually equal to 5 centimeter square. or in other words in the gate region the diameter would be 0.0252 meters. So, let us now calculate what is going to be the Reynolds number. As you know, Reynolds number is rho V d by mu, where rho is the density of the metal, in this case fluid metal, rho m, V is the velocity of the metal, d is the diameter of the cross section, which is actually the gate dia in this particular case, and mu is the kinematic viscosity of the material. Let me just write it a little more properly, rho m by mu. Okay. So, R e becomes equal to, in this case, 7800 kg per meter cube, which is actually given to be the density of the liquid metal, times of the velocity, which is 1.716 meters per second, times of 0.05252 meter diameter, divided by the viscosity, which is 0.00496 kg per meter second. And so, that becomes equal to a Reynolds number of about 68,000, which is actually determining the flow as turbulent, even though there is no wall friction, flow as turbulent. So, this is very interesting that the flow is seen to be turbulent by the first estimation without the use of any friction. Now, let us start the analysis. So, the flow is turbulent as at the first iteration, and thus obviously the first value of beta that you would take is 1, because as I told you, beta is equal to 0.5 if the velocity is in the laminar range, and when it becomes turbulent the beta becomes equal to 1. That is how the velocity losses or the kinetic energy losses because of the velocity distribution effect is understood from fluid mechanics theory. Also, we need to find out what is going to be the EF value in this particular case with an area ratio A2 by A1 almost tending to 0. As you can see here, the area of the upper sprue right here is much bigger in comparison to the area 5 centimeters cube of the gate or the sprue which is being talked about. So, the A2 by A1, where A2 is the point 2 and A1 is the point area at the point 1. 1 and 2 have different consequences. You may have just illustrated about this earlier as 1 here and 2 here, right about this. So, the 2 is always the lower cross sectional diameter. So, therefore, the A2 by A1 corresponding to 0 and the flow to be in the turbulent region, we have to read out the EF value from the graph describing contraction conditions. Okay. So, A2 is cross sectional area of the gate to be of gate, and A1 is the cross sectional area of the pouring basin. So, let us look at that graph which we had borrowed from earlier. So, let us go back to the particular two cases where for sudden expansion and sudden contraction you have a listing of the values of the EF, the friction loss and bending or fitting with respect to the Reynolds number 1, and also with respect to the area ratio A2 by A1. So, the A2 by A1 in our case is 0. So, it is tending to 0. So, we will have to read out really on this particular axis, and we are also suggesting that the flow in our case is actually a turbulent flow, and in the turbulent flow, as we have shown here or illustrated here, the Reynolds number that we have is close to about 68,000, which is actually somewhere in between these two values, right. So, one value corresponding to the EF at A2 by A1 equal to 0 happens to be close to about 0.5 and the other one is 0.4. So, somewhere in between here, by extrapolation of the EF values, you can have a EF equal to about 0.45 approximately. So, having said that, now if I have this EF equal to 0.45, let us go back, put this back into the CD equation and try to solve. So, EF is taken as 0.45 from the graph, okay. And we also know that for a turbulent regime, the friction factor or the wall friction basically is determined by the term 0.0791 divided by Reynolds number to the power of 1/4, as I had illustrated earlier, and this is actually plain and simple borrowed from fluid mechanics theory. I am not going into the details of how you obtain these, but we are wanting to see the application side of how you can design the casting once this is known. So, this happens to be equal to about 0.0049. So, that is how the wall friction effect would come. Length obviously is the length of the sprue side, because that is the lower diameter side, and in this case the total height that is there is about 0.12 meters, about 12 centimeters, as has been illustrated here. This total height from the pouring basin to the end of the gate region is about 12 centimeters. So, you are left with a value of CD. So, we have a CD value which is equal to 1, that is 1 by beta, plus the EF that is equal to 0.45, plus now you have 4 times of F, which is in this case 0.0049 times of L by D, which is the wall friction part of the problem. So, I can write this down as the total length of the smaller side, that is the sprue, divided by length of the divided by the diameter of the smaller side, that is diameter of the sprue, which is 0.0252 meters as obtained earlier. And there is a frictional loss because of bending, which has been given by this L by D equivalent of 25, as earlier illustrated in the question. So, you can see this L by equivalent to be equal to 25. So, that we add to this and compute what is going to be the value of CD, and this value comes out to be 0.7. So, therefore, the V3 dash or the velocity is going to be the CD times of root 2 g h t, as I had earlier illustrated the formula with friction of the energy balance. So, this is 0.7. So, it is 70% of the ideal case, which was 1.716 meters per second. So, this comes out to be about 1.20 meters per second. Okay. This is not the end of the story, because we will have to iterate to recalculate. So, actually the velocity is not 1.716, but 1.2 meters per second. Let us now recalculate with this velocity to just iteratively see what is going to be the change because of this change in the velocity because of frictional effects. So, recalculate the V3 again, V3 dash again, assuming the modified velocity 1.20 meter per second. Okay. So, let us for second approximation calculate the modified Reynolds number. So, this becomes equal to, obviously we can say it is just a length ratio or diameter ratio 1.2 by velocity ratio 1.2 by 1.716 times of the earlier obtained Reynolds number 68,000, which is about 47,500. Okay. So, obviously you know that Re equals rho m V d by mu. So, this V is changing from 1.716 to 1.2. So, this is the new Reynolds number value, and for this new Reynolds number value, if we look at again the regime is turbulent. So, the beta happens to be 1, the EF value happens to be about, in this particular case, slight improvements or slight change. So, let us go back to that graph again and try to understand what is the EF value. So, you have you had a value corresponding to 68,000, now you have a value corresponding to about 47,500. So, you can iteratively manage this by calculating it, and it will be slightly the higher side. This was the Reynolds number, that one which I am omitting is the Reynolds number 68,000 case. So, this will be slightly closer to the 10,000 Reynolds number. So, let us say it is on a little higher side, and you can extrapolate the value as that if in 68,000 the value was 0.45 and in about 10,000 the value is about close to about 0.5, then around 47,500 the value should be about close to 0.46, something to that light. So, just extrapolate between 10,000 and 68,000 and estimate what is the value of the Reynolds number at 47,500. So, this comes out to be about 0.46. So, 0.46 is the EF, the new EF value. We also have the wall friction F coming out as 0.0791 divided by the new Reynolds number 47,500 to the power 1/4 from fluid mechanics theory. So, this is coming out to be 0.0054, and if I compute what is the CD coefficient here, the CD comes out to be 1 plus the EF, that is 0.46 plus 4 times of the total friction factor, wall friction factor 0.0054 times of the L by equivalent on the smaller diameter side, which is 0.12 is the length, and the diameter of the gate is 0.0252. The bigger diameter is the pouring basin side, as I had earlier illustrated, plus the length equivalent which causes wall friction. So, that to the power of minus half, and this comes out to be 0.69. So, it is not really much different from 0.70, and you can say that the values have kind of converged. So, you can say that the velocity V3 in this particular case is very close to as obtained earlier. It is 0.69 times of the 1.716 meter per second. So, this is about 1.19 meters per second, which is quite close to 1.20 meters per second, which was obtained earlier. So, this is the converging step of the iteration, and I can say that iteratively I have arrived at a CD value close to about 0.69, which actually seems to be a reasonable estimation of the frictional factor in this particular case. Now, let us estimate, because of all these changes, what is going to be the time of filling of the mold. So, let us say the time taken in this particular case to fill up the mold, Tf comes to be equal to the volume of the mold divided by the gate area times of the velocity. This is how the volume flow rate would be. You know that there is an area of cross section A g, and through that there is a velocity emerging of the flow, which is V3. So, A g into V3 is basically going to be the volume rate of flow, and so you having the overall volume of the mold divided by the volume rate of flow is basically the time of filling. So, this comes out to be equal to 50 centimeters times of 25 times of 15 centimeter cube divided by 5 times of 1.19 or into 100, because we have to convert this into centimeters. So, 119 centimeters, and this is actually recorded as about 31.6 seconds. So, that is how the new filling time is, and you can see that in the ideal case the filling time was about 43% more than the case here. Okay. So, the filling time definitely has increased, and that is because of the energy loss which happens because of the bending and the different fittings and the wall friction and other issues. So, definitely in this particular illustration it is shown that the filling time goes down. Okay. So, I can conclude here that the filling time of the mold goes down as you neglect the wall friction effect. Okay. The filling time of the mold goes down as you neglect the wall friction effect, which is actually a very important supposition here. So, in all future modules, what we will do is we will estimate the filling time with reference to, in an iterative manner, just as I have done in this particular case, with reference to wall friction and also friction because of bending losses or losses in fittings. So, with this I would like to end this module, and in the next module we will do another very complex problem, where again all these effects are clubbed together to see what is the effect of the total time of discharge of a big pouring basin. Thank you so much.